Imagine a machine built around its most important component, yet somehow wasting its full potential. Electric cars are often described as the future of engineering, cleaner, simpler, more efficient. But what if that assumption is wrong? What if the very foundation of every modern EV is based on a flawed idea? Because right now, the heaviest, most expensive, and most technologically advanced part of an electric car is being treated like cargo. Not structure, not function, just weight to carry. And that raises a dangerous question. What if electric cars aren't inefficient because of their motors, but because of how they're built? And almost no one is talking about it. To understand why this problem exists, it's necessary to go back to how cars were originally built. For over a century, the architecture of the automobile followed a simple rule: separate everything. The engine was mounted to a frame. The fuel tank was placed somewhere safe. The chassis carried the load, and every component had a clearly defined role. Structure and function were never the same thing. And for internal combustion vehicles, that made perfect sense. Fuel is liquid. It moves, it sloshes, it burns. You don't build a car out of gasoline, so engineers designed around it. They created rigid frames, steel skeletons that could tamel stress, absorb impacts, and keep passengers safe, while the fuel remained just payload, dead weight, carried but never integrated. And that philosophy quietly carried over into the electric era. When the first modern electric vehicles began to emerge, engineers faced a new challenge: batteries. Unlike fuel, batteries are solid, heavy, dense, structurally stable. In fact, in many EVs today, the battery alone can account for 30 to 40% of the entire vehicle's mass. Which raises an obvious question. If the battery is already the heaviest and most rigid component in the car, why isn't it part of the structure? But early EV development wasn't about optimization. It was about safety, speed to market, and minimizing risk. So manufacturers defaulted to what they knew. They built a skateboard platform, a flat chassis, a reinforced battery pack mounted underneath, protected, isolated, replaceable, safe. And it worked. This design lowered the center of gravity, improved handling, and created a modular platform that could support multiple vehicle types. It was, in many ways, a breakthrough, but it also introduced a subtle inefficiency. Because now the car had two structures: one to carry the load, and another to protect the battery. Two systems doing similar jobs, but never working together. At first, this didn't seem like a problem, because the benefits of electrification, instant torque, quiet operation, lower emissions, were so overwhelming that the underlying architecture went unquestioned. But as EVs began to scale, as competition increased, as cost, efficiency, and range became critical, that hidden inefficiency started to matter. A lot. And this is where the story becomes interesting, because the industry didn't just inherit the architecture of the past. It may have inherited its biggest mistake. This is where the story shifts from design philosophy to hard physics. Because beneath every electric vehicle, there is a contradiction, a fundamental mismatch between what the battery is and how it's being used. The physics contradiction. In a modern EV, the battery is not just another component. It is the component. Weighing anywhere from 400 to 800 kilograms, it often represents the single largest mass in the entire vehicle. It sits low, spanning the floor, forming a dense, rigid slab beneath the cabin. From a physics standpoint, this should be ideal. Mass low to the ground improves stability. A wide footprint increases structural stiffness, and the battery's rectangular geometry makes it inherently resistant to bending. In other words, The battery already looks like a structural element, but it isn't treated like one. Instead, it is isolated, encased, reinforced, protected from the very forces it could help manage, which leads to a strange reality. The most structurally capable component in the car is not allowed to carry the structure. The traditional solution. To understand why, it helps to look at how EVs are actually built today. A typical battery pack is not just a collection of cells. It's a multi-layered system. Cells are grouped into modules. Modules are placed into a pack. The pack is enclosed in a rigid casing, often aluminum or steel, designed to protect against impact, vibration, and thermal events. And then, that entire pack is mounted into the chassis, which is also structural. So now there are two separate systems, one designed to carry loads, absorb crash energy, and maintain rigidity, and another designed to protect the battery from those exact same loads. Two layers of strength, two layers of material, two layers of cost, all stacked on top of each other. At first glance, this seems like good engineering. Redundancy equals safety. But in reality, it creates a hidden inefficiency, because both systems are solving similar problems independently. They don't share the work, they duplicate it. The real problem. And this is where everything starts to break down, because duplication comes at a price. First, weight. Every extra layer of casing, reinforcement, and structural support adds mass. Mass that doesn't contribute to propulsion, mass that reduces range. Second, cost. More materials, more manufacturing steps, more complexity in assembly. The battery pack alone already represents a significant portion of an EV's cost, often up to 30 to 40%. And yet, additional structure is built around it. Third, efficiency. Energy in an electric vehicle is precious. Every kilogram requires energy to move. Every inefficiency compounds over distance. So when the heaviest component in the car is effectively being carried, instead of contributing to the load, the entire system becomes less efficient. And finally, complexity. More parts mean more potential failure points, more interfaces, more fasteners, more tolerances to manage, which impacts reliability and scalability. And this leads to a quiet but critical realization. The battery is doing the least amount of structural work while being the most capable of doing it. It is treated like cargo, like something fragile that must be protected, when in reality, it could be the backbone of the entire vehicle. And this is the paradox at the heart of modern electric cars. They are built around the battery, but not built with it. And once you see that, it becomes impossible to ignore. Because the question is no longer whether this is inefficient, but why the industry accepted it for so long. And this is the moment where the industry begins to change direction. Because once the problem becomes clear, the solution starts to feel almost inevitable. If the battery is already the largest, heaviest, and most rigid component in the car, why not let it do the job it's already capable of doing? Not just store energy, but carry the car itself. Rethinking the battery. The idea sounds simple, but it represents a complete shift in automotive engineering. Instead of designing a vehicle around a battery, engineers begin designing the vehicle from the battery. This is the foundation of what's known as a structural battery, or more precisely, cell-to-body architecture. The concept removes the traditional boundaries, no separate modules, no heavy protective casing acting as an isolated shell, no clear distinction between battery pack and chassis, because they become the same thing. The battery is no longer something the car carries. It becomes something the car is built from. Architecture transformation. To understand how radical this is, consider what gets removed. In a traditional EV, cells to modules to pack to chassis. Multiple layers, multiple interfaces, multiple redundancies. But in a structural battery system, cells are integrated directly into a larger structural assembly. Modules are minimized or eliminated entirely. The pack casing becomes part of the vehicle's load-bearing structure, and in some designs, even the upper body of the car is bonded directly to this integrated battery system. The result is a single, unified architecture, fewer parts, fewer connections, fewer compromises. But more importantly, a system where every component contributes to both energy storage and structural integrity. Engineering deep dive. This is where the engineering becomes truly fascinating. Because integrating a battery into the structure isn't just about removing parts, it's about redefining how forces move through the car. In a conventional design, loads travel through the chassis. The battery is isolated, protected from stress. But in a structural system, the battery participates in load distribution. Forces from acceleration, cornering, and impacts are transmitted through the battery itself, which means the internal design must adapt. Cells must be arranged not only for energy density, but for mechanical strength. Materials must balance electrical performance with structural resilience. And the connections between components, often using advanced adhesives instead of traditional bolts, must handle both electrical conductivity and mechanical stress. Even crash safety is reimagined. Instead of shielding the battery from impact, the battery becomes part of the crash structure, absorbing energy, distributing forces, contributing to overall safety performance. At first, this seems counterintuitive. But when engineered correctly, it creates a system that is both lighter and stronger, because the structure is no longer layered, it is unified. Real-world impact. And this is where theory becomes reality. By eliminating redundant structures and integrating functions, structural battery designs unlock several key advantages. First, weight reduction. Removing modules, casings, and unnecessary reinforcements can significantly reduce overall mass. Second, increased range. Less weight means less energy required to move the vehicle, translating directly into improved efficiency. Third, improved rigidity. A unified structure increases torsional stiffness, enhancing handling and safety. And finally, cost reduction. Fewer parts, simplified manufacturing, shorter assembly times, all of which are critical as EV production scales globally. And this is why this shift matters. Because it doesn't just improve electric cars, it changes how they are built at a fundamental level. And once that happens, there is no going back. Because the question is no longer whether this approach works, but how quickly the rest of the industry can catch up. And this is where the gap between theory and reality becomes impossible to ignore, because not all manufacturers are moving at the same speed. Some are still building electric cars the traditional way, modular battery packs, separate chassis, layered structures, safe, proven, familiar, but increasingly outdated. Legacy automakers, shaped by decades of combustion engine design, tend to favor evolution over revolution. They adapt existing platforms, refine existing processes, optimize without fundamentally rethinking the architecture. And for a while, that works. But structural battery systems don't reward incremental thinking. They require a complete reset. And this is where new players and a few aggressive innovators pull ahead. Some manufacturers have already begun integrating batteries directly into the vehicle structure. Combining this with large-scale casting techniques, they reduce entire sections of the car into single pieces. Fewer parts, fewer welds, fewer compromises. The result is not just a better battery system, but a completely different manufacturing philosophy. Faster production, lower cost per unit, higher structural efficiency. And suddenly, the competition is no longer about range or horsepower. It's about architecture, about who can redesign the car from the ground up. Because once structural integration reaches scale, traditional platforms start to look inefficient, heavy, over-engineered, expensive. And this raises a critical question, not just for engineers, but for the entire industry. Is this an evolution of the electric car, or the beginning of something entirely new? Because if the structure and the battery become one, then the way cars are designed, built, and even imagined may never be the same again. For over a century, the automobile followed a simple philosophy. Structure carried the machine, energy powered it, two separate worlds, two separate systems. And for a long time, that made sense. But electric vehicles were never meant to follow those rules. Because for the first time in automotive history, the source of energy is solid, heavy, structural, permanent, and that changes everything. The question is no longer how to fit the battery into the car, but whether the car should exist without it. Because once energy storage becomes structure, the boundaries begin to disappear. Frames become unnecessary, components merge, complexity fades. What remains is something entirely different. Not a machine assembled from parts, but a system built around a single idea, energy and structure as one. And maybe that was the mistake all along. Not that electric cars are inefficient, but that they were designed to behave like something they were never meant to be. Because the future of the automobile may not be a car that carries a battery, but a battery that becomes the car.